This session is called ColdFormed Steel and MidRise Construction. Understanding the basics that are in this course will hopefully inspire you to consider ColdFormed Steel on your next project. This program will explore the use of ColdFormed steel assemblies in MidRise Construction. It is intended to provide instruction on the capacity of ColdFormed steel framed assemblies in both structural and non-structural applications in MidRise Construction. There are 4 learning objectives. The first, participants will explore the capacity of ColdFormed steel structure to meet the requirements for MidRise Construction. We will investigate building codes and standards for ColdFormed steel in MidRise Construction. Participants will learn some basic detailing techniques for using ColdFormed steel. And finally, we will look at some actual case studies and examples of MidRise structures using ColdFormed steel. What you're looking at in this top slide, and where the arrow is or the cursor, is coils of steel as they show up at the plants to make ColdFormed steel studs, joists, and so on and so forth. They have been pre-coated with a corrosion-resistant coating. The standard in the industry right now is a zinc, a hot-dip galvanization process where the steel is basically immersed in a bath of zinc and comes out coated. There's new technology coming that may change that, but the benchmark and standard in the industry is galvanization. Before we can start to make, let's say, a drywall furring channel, we have to know and slit the steel down to what's called its blank width. To do that, you have to imagine this furring channel here we completely flatten out. We've straightened out the hems that you see here, the ribs here, and make it one flat piece of steel. That's called the blank width. So we cut this huge coil of steel down to the blank width and mount it in front of this cold forming equipment here. Here you see a piece of steel that's just going through the cold forming process. It goes through a series of rollers and dies that gently form and bend that steel in the desired profile, which you can see the various profiles here, starting with joists down to studs, resilient channels, Z-girts, hat channels, angles, and accessories that are used in the construction industry. This steel comes in thicknesses starting in 18 mils or 25 gauge and graduates up farther to a total or the biggest thickness of 97 mils or 12 gauge. We're going to be talking this afternoon mostly in the C-stud joists or the S sections. This C is the standard profile that's used in ColdFormed steel framing, and I want to take a moment and just kind of walk through what I call the anatomy of a stud. And by that I mean, what are the various elements and what do they do to help this profile function as a stud? First, we have to realize that forming and shaping adds greatly to the stiffness of a profile. In other words, take a piece of paper, 8.5 by 11, and you try and stand it up on its edge, and it'll collapse. It cannot keep itself erect. If you take that same piece of paper and fold it in half, you generate stiffness and strength, and that is exactly what's happening in a C-shaped stud. This we call the lip, and the lip provides a very important function in that it provides stiffness to this element, which is called a flange. Without that lip, this flange would buckle under a load. And let's take a moment and kind of think through that. If I have load applied coming down from above, like this cursor is showing, on this flange, this profile then is put in what's called bending, where the top flange is in compression, the bottom flange is in tension, and they are the primary structural elements in resisting that bending, what's called a moment. The web, which is this element here in this case, is doing nothing more than keeping these two separated. The web plays a key role. As the load goes along the joist or stud, it must be transferred into the next, let's say the foundation, and to do that we have to concern ourselves with what's called in-reaction shear, and that's where the web plays a key role in the structural resistance and capacity of the steel stud. One of the unique features of a cold-formed steel stud is its unsymmetric aspect, and by that I mean it's not symmetric around its key axis, which would be this one here, the vertical one. And what happens is when you load it, as I described before on the flange, it wants to rotate around a point right around in here, which is called the shear center. And that's important, and we're going to discuss that a little bit more later on. But moving on to how we name the various profiles, there is a protocol in place to do that. And first we start with the member depth, which in this example is a 3 5/8 inch member, the decimal equivalent of which is 3.625, and put that in hundredths of an inch, it's 362. So the first descriptor is 362. The second descriptor is a letter, and it denotes the style. S as if it's a stud or a joist, T as if it's a track, U as if it's a channel, F as if it's a furring channel. We then look at the next series of numbers, 3, and it denotes the flange width, which in this case it's a 2.5 inch flange, which is denoted with a 250. The last number in the sequence is the material thickness, which is in this case 54 mils. The number is given in mils. If you're an old guy like me, that's 16 gauge. Moving on, we're going to talk about cold-formed steel capacity as it comes to the various elements. We're going to look at wall systems, the actual capacity of the cold-formed steel frame stud as a time-proven performance. I was very fortunate in my career in that I started my career in an R&D environment. And what a great place for a young engineer to kind of build things, twist things, burn things, and nowadays even explode them. But you get to see the capacities of the various building materials in a laboratory condition. And we always felt back in those days, and this is the early 70s, that the stud had a lot more capacity for axial loading than we were given it credit for. I can remember doing load tests on shelf brackets for a movable partition. The framing is steel, but the stud doesn't go from track to track. It stops at the top and the bottom and does not complete the trip. But the point of that is we could put 2,500 pounds on a shelf bracket on that stud, and it would not destroy the wall. And we would jokingly say, I could hang a Volkswagen off this shelf bracket. And admittedly, it was a 1973 Volkswagen, not the current Beetle. But the point is, there was a lot of underutilized capacity that we weren't using. Floor systems, we'll talk a little bit about that. There are many shapes and forms. Ultimately, though, the strength-to-weight ratio of cold-formed steel flooring systems make it ideal for mid-rise construction. They add a lot of strength without adding a lot of weight to the structure, which can be critical. Wind loads and limiting the amount of drift that the building will experience under a wind load condition is critical. We'll talk a little bit about that. And this is accomplished through simple things like shear walls and floor diaphragms. We'll look into fire performance of the various systems for walls and floors and show that cold-formed steel is non-combustible and is in its element, if you will, in mid-rise construction for fire and acoustic performance. On the wall systems, and kind of expanding on what I just said about supporting that Volkswagen, the point I want to make here is a 6 6-story steel frame structure that is supported on the lower floor by 6-inch deep stud framing. Admittedly, they're double studs, but they're 24 inches on center, and to me that truly speaks to the structural capacity of a cold-formed steel stud. On floor systems, there are many variations available to meet many structural requirements, and they're ideal for applications in live and dead loads found in multifamily construction. I was kind of looking at this slide, and it really points to me to the flexibility in design that architects can enjoy when they use cold-formed steel framing. Look at the differing steps. You got setbacks from one floor to the next. You have balconies. You have punched openings that are fairly good size, and cold-formed steel really makes it able to do what I call gymnastics to meet the architect's desire for the final design. If you look here, we have a cantilever here, we have a cantilever there, we have a cantilever here, we have this big box section coming out to pick up a cantilever which will be here. Huge punched opening here. Look at that long span header. That's I'm assuming that's at least a 2-car garage, and notice how the header is supported by jam studs directly underneath it. This really and truly to me points to the flexibility in design that can be accomplished when using cold-formed steel framing. Wind loads and allowable drift. The exterior walls must be designed for lateral wind loads, and the walls must also be designed to make sure that the wall stays in plane. The SFI technical guide has tables of combined axial and lateral loads up to 50 PSF. That means that a single stud system has the capacity to carry the structural loads of the building plus wind loads up to 50 PSF. That is for, if you look at this simple drawing down here, where you have the wind loads normal to that exterior wall, this wall in this case is goes into bending, taking care of the wind load, plus it's carrying the dead load of the structure from above. So that's combined stresses. Over on this side, where the wall is parallel to the direction of the wind, it must be designed so that in structural engineering you have to design what's called allowable drift. In other words, you have to restrict the building at the highest levels from moving a specific amount. Typically it's L over 500, where L is the height of the building. And that is from a structural standpoint, plus it is also from just a human response to when a building moves. But cold-formed steel framing can be designed as highly flexible to meet these requirements. Fire resistance. To me, first and foremost, all the elements that are used in the systems that I'm talking about are non-combustible. They do not support flame, they do not support fire, they do not contribute to a fire. So for that reason, let's say in wall applications, you can go from 1 to 4 hours very readily in both load-bearing and non-load-bearing applications. That's kind of interesting because when you think about a fire test and the high temperatures that the wall will have to withstand, it's over 1,000 degrees in the first 5 minutes of a fire test. The axial capacity of that stud, it has to hold up the whole building. On floors and roofs, over here you're looking at a floor assembly. It's got a concrete topping. We're looking at a steel truss floor system with a layer of gypsum board underneath. That qualifies for a 1-hour floor ceiling assembly. I can take it to 2 hours if I remove that concrete, put a metal deck and a cementitious topping above and 2 layers of drywall down below. Moving over to the roof ceiling assembly, we start at the top where you have insulation, a layer of gypsum board, a metal deck, a single cold-formed C-joist and a double layer of gypsum board underneath. That qualifies for a 1-hour floor ceiling assembly, which is known as UL Design P as in Peter 257. In acoustics, again, it's been my experience that the marriage of drywall, gypsum panels, and metal studs works extremely well in acoustics. There are 4 factors that contribute to the acoustical performance of assemblies, and those 2 prime components, steel and gypsum, work together and cover those 4 factors. Those 4 factors are mass, isolation, absorption, and decoupling. We have the mass, 4 layers of gypsum board. We have the isolation, which is the distance between here and here, which is given by the presence of the steel studs. We have the decoupling because this stud does not touch that stud, so these 2 assemblies are totally decoupled from each other. We have absorption in both cavities, yielding us up to a 66 STC. 50 is the benchmark of quality construction, so a 66, basically you're looking at walls that are designed for, let's say, theater applications. Same kind of level of performance in this guy down here. The difference is that it's a single stud, so you're saving some wall thickness, but you're adding a resilient channel to get the decoupling. In acoustics, there are 2 ways that sound travels through a structure. The first is airborne, and that's covered with sound transmission classification, or STC. The second one is IIC, and that covers structure-borne noise. Structure-borne noise is a little bit harder to control. Think of it as that marble tile floor and high-heeled shoes with a tenant underneath not wanting to hear the tap, tap, tap of the shoes. To design for that, you have to follow the guidelines that come up with an IIC, impact isolation classification, and the testing for that is kind of interesting. But the point I'm trying to make is cold-formed steel framed assemblies in floors provide excellent IIC characteristics. We will now explore the codes and standards that regulate the design of cold-formed steel frame structures. The standards were developed by the American Iron and Steel Institute and subsequently ANSI accredited. They are the North American specification for the design of cold-formed steel structural members. It is the premier document covering all cold-formed steel structures. The specification provides design methodology for determining the strengths, capacities of cold-formed steel structural members. A companion document, the commentary on the specification, provides detailed technical background knowledge to the specification itself. It is the basis for the development of cold-formed steel framing design standards. These standards are shown in the lower left-hand corner. It was first recognized there would be a logical hierarchy to these standards. So, starting with the specification and its broad focus on member behavior and design material thickness, the following standards were developed and ANSI accredited. The first one is the General Provision Standard. It is specific to light frame construction. Second is studs, joists, trusses, accessories for the repetitive member applications and material thicknesses between 0.0179 and 0.118 inches. The second pamphlet is Design Standards, which were developed to address issues applicable to system behavior and design that are beyond the scope of the specification. That is truss, header, wall stud, and lateral loads. The third pamphlet is a prescription method which was developed to provide builders with cookbook solutions. The fourth pamphlet provides general provisions and design standards that are applicable to both engineered or prescriptive design procedures. Now, moving on to the codes, we're looking at a table shown in the right side of the slide. This is taken from the International Building Code. The International Building Code essentially has two tables, 504.3 and 504.4, that must be reviewed to determine the allowable height of a building, as well as the accompanying amount of floor area that is also allowed. This is further modified based on the intended occupancy of the building. Examples of building occupancy include residential, building assembly, healthcare, and education. The tables also take into account if the building is made up of combustible or non-combustible materials, and if the building is to be considered sprinklered. One of the things I learned early on in this industry, and it's a famous quote that I use every chance I get, comes from Mies van der Rohe, and it's basically God is in the details. The corollary to that is equally important, maybe more important to us. The devil is in the details, which means to me, if you do a detail wrong, the devil's going to come out and have fun with you. Starting with the basic details, C-shaped stud wall studs installed 12, 16, 24 inches on center, which you can see in this slide here. They are capped with tracks. This particular track is on the bottom. This particular track is on the top of the lower framing. We have to apply some bracing. Remember I talked about rotating around the shear center? This is how we do that in a load-bearing application. In a non-load-bearing application, typically the wallboard gypsum panels installed both sides of the C-shaped stud is sufficient to resist that rotational tendency. In structural applications, and based on the fact sometimes a structural member experiences more stress under construction loads than it ever will under the design loads or the actual in-place loads. That means that this stud will be under load prior to the gypsum board providing the lateral bracing. So in those applications, we would suggest, recommend, require that cold-form channels going through the punch-outs that are physically attached to clip angles, shown here, that are attached back to the web of the studs. These are spaced vertically, third points, 48 inches on center, whatever the code requires. And if you don't want to do that, you can use, as mentioned here, flat strap on the flanges. I particularly prefer this one. Flat straps on flanges creates problems for the gypsum board down the road, but that's a design issue. Getting back to construction basics, how we attach the track to the slab. Use pneumatic or powder-driven pins is one option. Another option is a threaded anchor, where through the installation process the concrete is actually threaded, so this fastener threads in like a bolt. You can epoxy or use expansion bolts, or finally anchor bolts. Any one of these four will work given the conditions, the loads that are required, and the production rates that are needed. Definitely something that needs to be looked at by an engineer. Construction basics. Load path is something that is very important in any structural design, specifically through in cold-formed steel framing as well, and that means that the load in these joists, as it comes off the floor into the joist, it must transfer directly to the stud underneath. It must be a very clear load path. So we like to see things line up vertically on top of each other. You'll notice this little guy right in here. I talked earlier about how the web comes into play with interaction shear and web buckling. That's a web stiffener that may have to be used to transfer the load. If we don't have the capability because of design to do the direct load path, there are these options where you can use load distribution to transfer load back to the framing member or the stud adequately. In any building there are punched openings, be it archways, doors, windows, elevator doors, whatever. And there are many, many ways to handle the transfer of load as it comes down from structure above back to what are called the jam studs and down to the foundation below. In this particular example, we are using what's called back-to-back headers. They are two C-joists that are installed back-to-back with a track on top and a track underneath. They span from one side of the open to the other. Notice how they're directly over top, so you have that direct load path down to the jam studs below. We call these, or at least we used to call those cripple studs, and they're just an infill, so you get down to the rough opening you need for your punched opening. This is just one option. You can use boxed headers, as you saw on that slide earlier. You can use maybe one joist, two joists, 3, 4. It depends on how big the opening is and what the load is coming down from above. Many, many options are available. There are also many options available for resisting that lateral drift. Probably the most traditional is sheathing, be it plywood, OSB, or gypsum board. The next one would be flat strap installed in an X-bracing configuration, which you see there. Steel strapping works very well in tension. It doesn't work so well in compression. It's like pushing on a rope, so therefore we have to put it in an X configuration. Another option is a steel sheet, as you see here, and the fourth option is integrated panels that have the steel sheet right into the panel itself. Pre-engineered trusses or C-rafters can be used for roof assemblies. The pre-engineered allows you to go longer free span openings. It also opens the door for panelization, which we'll see in our case studies was critical from a performance and a production rate standpoint. Or you can use the C section in a rafter configuration. Shown here is the old-fashioned hip roof, which can only be done in a rafter configuration, as you see here. The rafters allow you to do nice cathedral ceilings. The downside of the truss is it does chew up a lot of height and may put some limits on your interior design. Construction basics for floor systems. What you're looking at here is the generic C-section, joist and track, in a simple span condition. Again, here's your load path, joist coming in, the web stiffener going down to the floor below. There are also proprietary sections that are out there that have huge punched openings in them that will easily accommodate MEP, and this may be something really worthwhile to look into. Another option for floor systems is to go to a floor steel truss. Again, we have then a very lightweight structure that can be used for long spanned applications, greatly impacted by panelization, and really can work into your production schedule. Really accommodates MEP runs. The downside is, again, it chews up a little bit of elevation. Toppings, you have two primary choices. You have combustible or non-combustible. Combustible being plywood, OSB, fire retardant treated wood. On the non-combustible side, we have corrugated metal deck with a poured cementitious topping. We have cementitious sheathing, or you can use the good old-fashioned composite steel deck with poured concrete as shown in this application.
The next series of slides will cover a conceptual design of a high-rise building that was designed using cold-formed steel framing. The design was completed by Matson Ford, a structural engineer based in Milwaukee, Wisconsin. The tower itself is a type R3 apartment complex, and throughout the building, conventional building materials were utilized. What's most important in this application or in this design is the use of generic profile cold-formed steel framing members. Those are the profiles that I described earlier. The physical description of the project is as follows. The story height was 10 foot. Demising walls were spaced 25 foot 6 inches on center. There were 2 stairwells and 1 4-elevator central core. Both the stairwells and the elevator core used poured-in-place concrete primarily for its shear capacity and wind resistance. There was also a central corridor that ran throughout each floor plate. Looking at the individual elements that went into the tower, 6-inch standard C studs were used throughout. The floor joists were 12-inch C-shaped joists. The spacing of both the studs and the joist vary from 24 inches on center at the higher floors down to 12 inches on center at the lower floors. The roof deck consisted of metal deck with a lightweight EPDM system on it. Each floor used 1.5 inch poured gypsum concrete on metal decks. Lightweight exterior finishes such as EIFS was used on the exterior, and the balcony system used aluminum post balconies at each floor level. The next series of slides will cover some standard details, in this case using brick veneer, taking us from the roof parapet down through the foundation. We'll look specifically at those details that utilize cold-formed steel framing and meet and are compliant to the latest energy codes. We'll look specifically at the roof parapet, window head, window jamb, window sill, intermediate floor, and then the foundation. Here is the roof parapet. We see that the exterior load-bearing steel framing is framed in a balloon type fashion where the roof members, which are common C joists, are tied in through a rim track tied to the back flange of the studs. We can see cavity insulation fully filling the stud cavity. We see gypsum non-combustible sheathing, a water-resistive barrier, continuous insulation in the form of extruded polystyrene, the brick ties which are tied back through the gyp sheathing and into the steel framing below, and then the brick itself. Over the top is coping, and what is important from an energy engineering standpoint is that the air barrier be continuous without breaks coming from the roof up behind the back side of the wall, over the top of the steel framing, and then down the face of the gyp sheathing. This is done using standard either peel and stick type air barriers or the liquid applied type. Moving down to the window head, We can see that we have a boxed header to transfer the load over the top of the punched opening, carry it back to the jambs on either side, or on both sides, and then down the side. We can see flashing the lintel for the brick tie, and the continuous insulation in this application. The insulation, by the way, for the boxed header, there should be insulation within that space, but it's eliminated here or omitted here just for clarity to show the box configuration of that header. Moving to the jamb, we can see we've used a double jamb stud on both sides of this window, and they are also in a box configuration and with the insulation omitted from the enclosed section created by the box jambs themselves. Moving down to the sill of the window, we see the details that are required to make sure that the continuity of the air-water barrier is maintained. And you notice in this case that we've used wood blocking to wrap around the punched opening and tie into the ColdFormed steel framing. Some contractors prefer this type of application for they feel it's easier to install the windows. It basically is an option as far as I am concerned. On an intermediate floor basis, we can see that the floor system is tied in to the balloon framing. We break the framing, the steel stud framing, just above the floor line. The cavity of the studs is filled with insulation. Again, gypsum board on the inside, gyp sheathing on the exterior side with a WRB area barrier, continuous insulation, brick ties, and then the brick itself. Coming down to the foundation, we see that the ColdFormed steel framing is bearing directly on the foundation itself. There is sealant to adequately seal the bottom of the gyp sheathing to the concrete slab to maintain an air barrier or maintain tightness for the structure itself. WRB comes down over the face of the flashing that we see coming out to make sure that we have adequate draining from on the exterior side of the extruded insulation, as well as any water that might get in a liquid state through the extruded insulation to the backside, protecting the water sensitive materials such as the gyp sheathing. We're going to look at some more basic details that are specific to the interior of a load-bearing structure, mid-rise in this case, and from it we're going to pull from the details that were generated for the Madsen Tower, which we discussed earlier. These details shown here are common to the design of mid-rise construction, so very appropriate and applicable for this presentation. In the upper row, furthest to the left, we're looking at lateral bracing of the floor joist system, ColdFormed steel C-shaped joists being laterally braced by a combination of flat straps, top and bottom, and then solid bridging. Moving over to the center detail on the top row, we see an interface of a floor framing system to the load-bearing steel framing behind it. What's important to note in this detail is that the studs, the vertical studs, are vertically aligned from the upper floor through the lower floor. This is done to ensure the most efficient load path for the gravity loads from roof down to foundation. Going to the lower row and furthest to the left, the designer has opted to use welding to attach the cold-formed steel studs to the bottom track. The designer could have opted to use mechanical fasteners such as screws, but in this case chose welding. The point to be made here is that that is an option from a design standpoint, either to weld or mechanically attach stud to framing. The center detail on the lower row shows how to handle the differential spacing from one floor to the next. The upper floor, the studs are spaced 24 inches on center. On the lower floor, they're 16 inches on center. And to adequately carry the load between those two framing spacings, a distribution beam or distribution joist is used in that center line that you see there, horizontal line. On the lower right is pretty much the same detail as in the upper row, but in this case we're getting floor framing from both sides of the load-bearing wall. But again, notice that as much as possible, engineers prefer to have the studs vertically aligned as we transition from floor to floor.
Now we will look at two case studies. One is on the west coast, the Poly Canyon Village student housing in California. The second one is up near Toronto, and it's the Sheraton College. Poly Canyon student housing. The owner is Cal Polytech. The project team was Niles Bolton, NVE Institutional of Irvine, Clarke Construction, and the installer of the cold-formed steel framing was KHS&S out of their California office. I had the pleasure to walk this job when it was under construction, and it was a really, really amazing project. The irony is I have really no clue why I was out in that part of the world. I can't remember who I was seeing or what I was doing. But I did go there with a local rep of the company I worked for and walk the job. And I was so impressed with it. I remember that, but not the reason I went to California. But anyway, at the time, and I'm sure it's still true, it was the largest cold-formed steel project in California. It was housing for 2,700 students on a 30-acre site. It had 820,000 square feet of 11,000 load-bearing panels. The original construction schedule called for a 20-month construction cycle. It was shortened to 14 months using cold-formed steel in a panelized application. The project earned LEED points because of the cold-formed steel recycled content and the fact that it was panelized locally, so it was a regional material. This is a quote from Mark Blackman of Clarke Design. "I would absolutely use the system again, especially for these kinds of projects. The manpower on site, along with faster construction schedule, makes the system with cold-formed steel ideal for low-rise and mid-rise multifamily construction projects."
This particular case study is on the Sheraton College student residence in Oakville, Ontario. The project itself, the owner is...
This concludes the formal part of the SFIA presentation.
Out of London, Ontario. The steel engineer and fabricator was Magis Building Systems, and the fabricator was Nucor Steel. The building itself was designed for 6 stories, 186,000 square feet. It was designed to house 250 students with an installed cost of $25 million. The steel framing ranged from 33 to 97 mil. What was unique or what made this project really successful was the combination of the panelized exterior walls and hollow core concrete floor system that was used throughout. This project had a very tight construction schedule, further compounded by the fact that its schedule called for erection of the cold-formed steel framing and floor system in a Canadian winter season. Therefore, the use of the panelization, cold-formed steel framing, and hollow core floors really allowed for that winter construction and allowed the project to get done on time and under budget.